Welcome to another RDWorks Learning Lab. After a long while away preparing the previous video and all the data that went with it, I've been able to sit down and study that data. The PDF file that I issued with that data clearly says this is not the end. This is just the beginning, because all it's doing is documenting a huge range of tests to see if there's any pattern that we can see that will help us to answer two questions. Why is it that the cut sides are parallel when, regardless of the focal length of the lens, you would anticipate something other than that? And the other question is, why is it that with all the same parameters, different materials do not respond the same way to the same lens or the same cutting speeds? I believe that the first question, why do we get parallel-sided cuts, is the most difficult question to answer. But as I've been looking at all the results that I've produced, one thing has become obvious. I spent quite a bit of time mapping the energy density profiles of different lenses. It wasn't a waste of time because it was interesting, but I don't believe it bears any relevance to the question that I asked. I was hopeful that there is a relationship between the energy density graphs and the shapes of the cuts that I was going to produce. But today, I've had a little bit of a brainwave as to how we might try and narrow down what's going on and how we manage to produce parallel cuts. So, come on in. We're going to have a look at one of my childlike doodles to see if I can explain what's up here in this maggoty mind of mine. So wherever you look on this set of results for MDF, and I've chosen MDF because the black lines are much easier to see. This being a plano convex 1.5 inch lens, flat side down. Here it is dropped 3mm into the material. Then it's flat side up, dropped 3mm into the material. Then we've got a meniscus lens, flat side down, dropped 3mm into the material, flat side up, dropped 3mm into the material. Now, wherever you look down those 1.5 inch lenses, regardless of orientation or shape, you produce parallel holes. The same applies to the 2.5 inch lens and the 4 inch lens. There's a slight difference in the beam thickness and the line thickness, but that's not the point. The point is we're producing parallel sided holes. Now, passing through 10mm, which you certainly wouldn't want to do with a normal 1.5 inch lens, that's absolutely staggering. So today we're going to try and see if we can find out what's going on inside the cut. Okay, let's begin with a couple of basics. Laser beam, lens, light passing through the lens, travels in straight lines, and we'll just draw the extreme rays like that. This point here where the rays cross over is called the focal point. This distance between the lens and the focal point is called the focal distance, and for the purpose of this simple exercise we'll choose a 1.5 short focus lens, 1.5 inches, which is equivalent to 38.1mm. Now, at the focal point there is a theoretical area called the spot size. Now, that's the area through which every single ray of light theoretically passes, and that is dependent upon the wavelength of the light. So depending on the focal length and the wavelength of the light, there is a theoretical spot size. Now, all I can say to you is it is theoretical, because in practice, with all the tests and work that I've done plotting the energy density through the lenses, and also this current work where we've looked at things like the width of the beam entering and leaving, I can tell you that it's anything between ×2 and ×5 bigger than the theoretical spot size. So ignore what the book says and just live in the real world. Now for this 1.5 lens, you would expect a spot size normally of around about 0.075 millimeters. Now the best that I've probably been able to achieve is something closer to 0.2 millimeters. Well, that means that when I focus the lens down onto the surface of the material, and there's the surface of my material, at that point there we have 0.2 millimeters diameter. That effectively determines the entry size of the beam as it enters the work. Let's just back up 1 second and go back to something that we've talked about many times before, and that's what's happening in this laser beam itself. The laser beam is invisible to our eyes anyway, and it is still a beam of light energy. But the light energy across that beam is not uniform. Now what you're seeing on the screen at the moment is a simulation of what this beam is actually doing. You'll notice it's got very high, bright, intense centre to the beam, and it drops away to 0 intensity on the outside. Well, that's what's happening in this beam here. We've got 0 light right at the edge, almost 0 anyway. Then it goes to an intense light in the centre and drops off back to 0 on the other edge. Now, this is not the shape of the beam, I hasten to add. I'll just draw a line across there to indicate that it is a graph of the intensity of light within the beam. Now that graph could equally well be drawn the other way. It makes no difference. It's just a depiction of the intensity of light within the beam itself. And that's the most important concept that I want you to grab and hold on to here. Because when we focus that light down, and I'll just borrow one of the lenses out of my wife's glasses. Now the unfocused light looks like that. But as I concentrate the light, you'll see that it's just getting smaller and smaller and much more intense in the centre. If this picture here represents the intensity of the light relative to 0, at this point here, where I've focused it down, the intensity of the light is much, much higher. In other words, if I have to draw the same graph at this point here, it's going to look like this. It's still 0 at the outside, but the intensity of light at the centre is much greater. So effectively what I've done, I've made the beam, this is not the correct term to use, but imagine it as more pointed. It's much, much higher intensity light at the centre of the beam when it's focused. So it's able to do much more damage here than it was when it was here. Now when we started off at the top here, the raw beam was about 12 millimeters diameter. And then we've compressed it down into this spot size here, 0.2, and as I've just demonstrated to you with this lens, the light has become a lot more intense. And that means that this picture now is no longer X, but it's X times 1,000. That very, very high intensity light is able to do a lot more damage than the light at the outside edge of this focal point. Now, we've still concentrated all the energy into this area, but it's not uniformly concentrated. So we've got tremendous potential for doing a lot of damage right at the centre. Well, how does all this fit into the scheme of things? Let's move on to another piece of paper. I've got some 10mm material, and I am going to be firing the laser beam at spot on the surface, the focal point. My theory is this. At that point there, we've seen that we've got this incredibly high energy distribution at the centre. We're going to see a mode burn which effectively looks like this. cut, what's going to happen is this. By some miracle, once the beam has entered the material, it never changes its shape. It continues to come down here like this, leaving a parallel hole behind it. And then it gets to the bottom here and it breaks out. And at that point there, we've got a cut. But what we've also got left behind is the end of the point of the beam. I call it the point of the beam because it isn't really pointed, it's just got this high energy density centre part which is doing the most damage to the material. And once the damage has come out the bottom of the cut, you are happy to say, right, that's it, that's the right speed for cutting. Now the reason why I'm coming to that conclusion is because when we look at some of these images close up, you'll see that every one of them has got a little teeny weeny cut at the bottom. All of a sudden it closes up. We've got a cut which may be 0.2, 0.3, 0.4 down the middle here, and yet just at the bottom here, the last millimetre or so, we've got cuts that close up. i.e., here's a reasonable explanation as to why that cut closes up at the last minute. Now, when we run at very, very, very slow speeds, as we did on this first and second test here, you will see that the cut is actually fairly uniform all the way through. In other words, where we've got loads of excess power, the time taken for the power to burn its way through the material is sufficient that this high energy breaks out the bottom here, like this, and actually leaves the parallel cut behind. After studying these pictures, that's the sort of mechanism that I imagine might be operating here. How on earth am I going to prove this? I don't have a high-speed camera that can watch the cut being generated at 12,000 frames a second. So I have to be a little bit inventive in the way in which we can try and observe what's going on. But I think I might have come up with a solution. Well, here I've got some 10mm acrylic, and I'm going to first of all cut out a nice clean 25mm square. I'm also using this extruded acrylic because that will give me a chance of a better edge as well. That's a pretty good mirror edge, so we can see through the acrylic cleanly. Now, to carry out this test, I'm going to use a couple of features on this machine which aren't very often used, so I'll just show you what they are just in case you've never come across them before. If we press the ZU button and we go down to laser set, enter, we shall find that we've got either the opportunity to do continuous, which is probably how your machine is set, which means when you hold the pulse button on, the pulse stays on all the time, or the other option is manual. And underneath manual we've got another little window which, if we press the ZU button again, we can access, and it's in milliseconds. And what we can then do is when we press the pulse button, no matter how long we hold the button for, we only get an X millisecond pulse. So I'm going to set that in the first instance to 5 milliseconds. So 4, 5, and there we go, 5 milliseconds, enter. Now the other thing that we need to check and set, and this is a very useful feature as well for doing this sort of work, and that is the one above it called manual set. And it's virtually the same, but instead of working with the laser, it works with the XY buttons. So again, we've got manual and we've got continuous. Again, your machine will generally be set to continuous so that you can drive your buttons, you can drive your head around however you want it. If you turn it to manual, press the ZU button, underneath we've got the opportunity to set a manual number of millimeters. And I've got mine set to 1 millimeter now, So that means every time I press the down button or the up button or the left or the right button, the head is only going to move by 1 millimetre at a time. Okay, so in the corner of the machine, I'm going to place one of my Perspex squares. Okay, so I've just reset the machine now away from 5 milliseconds to 1 millisecond. So the very first pulse that we're going to put on that piece of material is 1 millisecond long. And there we go. Now I'm going to move the head towards me by 1 millimetre with a step. ZU button, laser set, enter, step down and change the pulse length now to 2 milliseconds. Enter, escape, pulse, step. Now we go through the whole routine again. So I'm not going to bore you with that. I'm going to produce a pattern of data and then we're going to look at them under the microscope. Okay, so what we can see on the screen here now is the first 10 dots that I did. Now, I say 10, if you count back from the right hand side, you'll find there's only 9 on there because 1 millisecond did not have any impact on the material at all. So the first dot on the left there is a 0.2 millisecond dot. And I'm looking at it from above, obviously, so that we can see that it is 0.2 of a millimetre diameter. The last dot at the right, I think we can see is about 0.5 diameter. Now if we work back from number 10, which is what that is, that's 10 milliseconds, 9, 8 milliseconds, they're all about 0.5 diameter. And after 8 milliseconds, they start decreasing in diameter. Now that's obviously the beam growing as it gradually penetrates into the material. We'll look at this from the other view in a minute, but you'll see what I mean. But it's important to note that 10, 9 and 8 milliseconds are basically stable diameter. Now here's the same set of 9 results, but looking from the side. The bottom one is 10 milliseconds and the top one is 2 milliseconds. And as you can see, 2, 3, 4, 5 and 6 are growing in length, but they're also growing in diameter and they've got a tapered look to them all the way. And it's only after 8, 9 and 10 you can begin to see a little bit of parallelism appearing on the left hand side, i.e. at the entry. So what I'm expecting to see as we carry on with this series is shape number 7 sitting at the end of a parallel hole. Now here we've got 11 milliseconds through to 20 milliseconds, and we've got an interesting development taking place here, because not only have we got the number 7 shape sitting on the end of a parallel hole, as we progress down this series, the parallel hole only reaches almost a certain length, and then it starts to grow into a secondary, much larger diameter hole. By the time we get to 15 milliseconds, we've reached a fairly stable secondary parallel cut. So what's beginning to happen at number 15? Well, I'm proposing the following. The laser beam is busy trying to bore its way through the material. Now when I say bore its way through the material, I mean what it's doing, it's heating up the material in front of it and it's turning it into a vapour. Now a vapour takes up substantially more volume than the solid that was there before it. So that vapour has to escape somewhere, and the only place for it to escape is out of the hole. So the expanding vapour is coming out of the hole and it's meeting the laser beam coming into the hole. The definition of vapour is solid particulate matter suspended in a gas. Fog, steam, they're water particles suspended in air. These are acrylic particulate suspended in a gas. Now, anything that is solid is going to be affected by the laser beam. The laser beam is going to impact them and heat them up again. So what we've got secondary heating of the vapour around the laser beam, and that is causing this expansion of the diameter. So we've got the beam going one way and the hot gas probably going in the other direction. As you can see, from number 15 onwards, we've got a fairly stable, larger hole. Here we're jumping to the end where I think we've got 48 milliseconds at the bottom of this page. Now I think you can see that everything is settled out and stabilised very nicely. The only thing that's changing is the depth. And to be honest, as they're getting deeper, the rate of change of depth is decreasing. So I think this becomes obvious when we can see the whole series. As the hole gets deeper, so its rate of progression is decreasing. It's probably losing more and more of its power to converting more vapour into heat. I'm asking myself, can I verify this in any way? Okay, now if my theory is in any way credible, it's got to stand up to this test. Here I've got a thickness of material 10.2, but it's made up of 5 pieces of 1.6mm acrylic, each one is spaced apart with a 1/2 mil washer. So at every 1.5 millimeters I've got an escape road for the gas. So there's no way that the gas is going to build up in there except in the very, very small sections. So I would anticipate that I should technically get a much smaller burn hole. So we only need one test at 50 milliseconds to prove or disprove the proposal that I've just put forward. Now you can clearly see the fumes have escaped between the sheets because look, we've got white debris that wasn't there on previous tests. Well, here is the result. Very interesting. Now I've measured the second section down and that is 0.5, exactly the same as the previous results. The only thing is there's a very big difference in the shape of this tube or the form of this tube. If you look carefully you'll see there's a very thin pipe right down the middle. But round the outside of it we've got what I would class as a heat affected zone. They're like micro bubbles. They're not actually scavenged away like the previous test that we did. So I think we've got rid of the gas dynamics in there. So I think what we've got here is some sort of follow-up effect of the beam where the follow-up is actually heating and liquidizing the surface and creating bubbles. It's not actually creating enough heat to gas it away as it did previously and scourge it away. So we'll have a comparison in a minute. Now the other thing that I want you to note is the way in which it's really strange this, because one of the other things that I will be testing at a later date is a strange effect that I came across whereby although the beam comes in and it appears to sit parallel within the tube, as soon as it escapes out the bottom surface of the cut it starts to diverge. Well, here we've got 1, 2, 3 diverging areas for the beam to start doing something silly. Can we see evidence of that? Well, between the first and second interface there could be a small increase. Between the second and the third, again, it's difficult to say. I'm looking for something that I'm anticipating and I can't really see it. There's hints of it there but not clear evidence. It was a risk when I set this up that I would completely destroy the cut. This is a comparison of the depth of cut. Now the thickness of the material on the right hand side should be 10 millimeters, but in fact when I measured it it's about 9 millimeters, and the one on the left hand side is about 10.2, so that's why there appears to be a difference in the thickness of the materials. Now this picture tends to substantiate one of the proposals I made earlier, that the expanding vapour escaping from the hole on the right hand side was hindering and absorbing some of the energy that was coming in from the laser beam, and that in turn was affecting the depth of cut. And when we look at the left hand picture we can clearly see that without the hindrance of that gas the beam has actually gone 15-20% deeper. Now I apologise for the strange angle, but at least we've got both sets of results in one picture. So I think these pictures, when you look at them side by side, show that there's a definite difference in the mechanics that's going on inside the cut. The one on the top is definitely got some lovely scavenging in there, gas dynamics, that isn't in this bottom left-hand cut. So the one that's real, that we normally experience, is obviously the one on the top right there. So what we'll do, we'll see if we can compare the shape of those beams with the cuts that we've been getting in our materials. I have to apologise because my wife stopped me doing all this important work, dragging me off to Rhodes for a relaxing week in the sun. Now it was very nice because the temperature out there was 30 degrees C. I was sitting by the pool all day. She had her headphones on listening to audio books, and I had my head full of all these images trying to solve why beams cut the way they do, why lenses work the way they do. So I had a great time because I was there on my own, effectively playing with my machine in my head. So here we are back in England, and today it says on here 12 degrees C. Yeah, it's a bit of a change from where I have been. Now the good news is I'm not going to do any more testing, because while I was on holiday in a semi-comatose state most of the day, laying by the pool, sipping coffee or wine, I had a revelation. I think I understand how lenses work now. The work that I've done so far has enabled me to unravel the fundamental question of how the laser beam works in a cut and why different materials react differently to the laser beam. So I'll see you in the next session when all will be revealed.